This lecture, is on a technique called the method of lines. And if you followed the lectures on transfer matrix method and rigorous coupled wave analysis, I think what you'll discover is this is nothing new. This is really just the transfer matrix method again with multiple dimensions. With rigorous coupled wave analysis, we used a Fourier transform. Here we'll use finite differences, similar to finite difference frequency domain. So the outline of this lecture, because really, as you'll find, you know this technique now, having been through rigorous coupled wave analysis and the transfer matrix method. So I can very quickly then step through the formulation of a 3D method of lines, fully three-dimensional, which would be equivalent to what we did with rigorous coupled wave analysis. And what's more commonly seen in the literature is a two-dimensional implementation. At the very end, you'll see why that is. And very quickly how to handle multi-layer devices using scattering matrices. And you'll find this exactly the same as with transfer matrix method and rigorous coupled wave analysis. So the method of lines, from a purely mathematical perspective, it's a technique where we discretize all of the independent variables except one. For electromagnetics, usually we'll let that be the z parameter, but we discretize x and y. And then we solve the z direction analytically. And this is exactly what we did for rigorous coupled wave analysis. We used a Fourier transform there to discretize x and y. And we left z analytical, and we solved that differential equation analytically. And that brought us a lot of benefits that the method of lines also shares. So from a purely mathematical perspective, rigorous coupled wave analysis is the method of lines. It's just in Fourier space. In this lecture, we're going to learn another implementation of method of lines where we discretize x and y using finite differences. We could just as easily discretize x and y using finite element or a number of other numerical methods. But in computational electromagnetics, when we hear the word method of lines, that seems to imply that we're using finite differences to discretize our variables. But from a mathematical perspective, rigorous coupled wave analysis is also the method of lines. It just uses Fourier transforms instead of finite differences. So let's talk about how to formulate a fully 3D method of lines. Just as in rigorous coupled wave analysis, we are going to model something that's periodic, and I'm showing an extended lattice in the middle. We will extract a single unit cell, and we will look at the cross-section of this. So what I'm showing here on the right is a cross-section of a unit cell. So we'll decompose our structure into a number of layers, where each layer is uniform in the z direction. We will analyze the cross-section, and we will essentially calculate all the modes that exist in the cross-section where we can propagate those analytically, just like what we did for rigorous coupled wave analysis. So this should be a very familiar starting point. We have our 6 Maxwell's equations coming from the curl equations, and we've normalized our magnetic field according to this lower left equation, and we've also normalized our grid by multiplying by k naught, which is essentially the same thing as dividing by wavelength. So our normalized grid coordinates are unitless. From there, we are going to analyze Maxwell's equations as if we are in the smack middle of some structure, some layer that is perfectly uniform in the z direction. It can have whatever complexity it wants to in the x and y plane, but it's perfectly homogeneous and uniform in the z direction, and we are analyzing electromagnetically the cross-section of this. So I'll call that a z uniform media. So in a z uniform media, we can take Maxwell's equations. We will then approximate the x and y derivatives using finite differences, and we will leave the z derivative analytical, very similar to what we did for rigorous coupled wave analysis. But now we're equipped, having been through all the finite difference stuff, to jump immediately from our analytical differential equations to finite difference equations. However, these still contain an analytical z derivative, but we have a set of matrix equations, if you will. And as you recall from finite difference method and finite difference frequency domain discussions, we have these lowercase letters. So H, this will be a column vector containing all the x components of the magnetic field. Likewise, this bold E, this is a column vector containing all the y components of the electric field, and so on. And of course, here's our derivative operators. These are banded matrices that calculate derivatives across a Yee grid, so we'll be adopting the Yee grid here as well. Not surprising, what we'll do now, our 6 equations are now on the left. We will take the third and sixth equation and solve for the longitudinal components, the HZ and EZ components. We'll now take this expression for HZ and plug that in to replace HZ here and here. We'll take our expression for EZ and we'll plug that in here and here to replace EZ. Now we end up with 4 equations without EZ or HZ, and we've also brought the analytical derivatives to the left-hand side and everything else to the right-hand side. So we have 4 equations now, 4 matrix equations with an analytical Z derivative. So we can take our first 2 matrix differential equations and write them in block matrix form, and we end up here. We can take our second 2 matrix differential equations and write those in block matrix form, and we have what we're showing on the lower right here. Now we can jump to our standard PQ form that we saw for transfer matrix method and we saw for rigorous coupled wave analysis. It also popped up in waveguide analysis. Well, here we are. And so these equations really are just like what we had for rigorous coupled wave analysis, except instead of having the field components directly, we had amplitudes of our spatial harmonics. So we had S's in place of E's, and we had U's in place of H's. Otherwise, we're at the exact same form. And what you'll see from this point forward, the implementation and formulation of the method is exactly the same as transfer matrix method and rigorous coupled wave analysis. So other than how P and Q are calculated, really these are all the same method and implemented the same way, and we can literally copy and paste our code for transfer matrix method or rigorous coupled wave analysis and be implementing method of lines. So of course our next step once we get to PQ form is to derive a matrix wave equation. Well, what we can do is we can start off with the P equation and calculate a derivative. So we end up with a second order derivative on the left. P is not a function of Z, so it comes to the left side of this derivative operator. And what we're left with on the right is the derivative of the H fields. Well, if we look at our Q equation, we have an expression for the derivative of the H fields. It's just Q times the E fields. So we can put this expression in place of the derivative of the H fields. And now we end up here, we have a second order matrix differential equation that we can write in a slightly different form. We can write it this way, and now again we have something almost exactly like what we saw for rigorous coupled wave analysis. We just have E's instead of S's because these are the actual electromagnetic fields at each point in the cross section instead of amplitudes of spatial harmonics. But our omega squared matrix is still P times Q. We derive our P and Q a little bit differently, but once we're here, the algorithm is implemented the same as rigorous coupled wave analysis and transfer matrix method. So we want to solve our wave equation. Well, we have the solution of the same form that we saw for rigorous coupled wave analysis. And so then we can immediately write the form that also includes the magnetic field. So this solution contains all 4 of the transverse field components. We're still missing EZ and HZ, but we can write our solution this way. And we can calculate the eigenvector matrix using our well-known formula at this point, QW divided by lambda. And really, you know the rest of the story to this. The way we interpret our solution is the same. This psi parameter, these are our overall fields. These are the things that we can look at and see pictures of fields. This W is our eigenvector matrix. That tells us, if we look at that, we'd see pictures of the modes that would exist in the cross section. This exponential term describes how those modes propagate. Do they grow? Do they decay? Do they oscillate? And then the C term tells us how much power is in each of those modes. And this is exactly the same as in rigorous coupled wave analysis. Another picture that's exactly the same is trying to illustrate what's happening inside of a semi-analytical method within a layer. So we've essentially analyzed the cross-section, and we calculate all of the modes that exist in the cross-section. So our modes, or the picture of the fields, is described by an eigenvector for the electric fields, an eigenvector for the magnetic fields, and then that just tells us on a relative scale of what all the field components look like. We need to know the overall amplitude to know how much power is in that mode. And each mode gets its own amount of power. We have not only the forward modes, we have all the backward propagating modes. These are the same, they're just propagating backward. So this is how we visualize the solution within a layer for a semi-analytical method. Now let's talk about the formulation for a two-dimensional method of lines. What you'll see at the end of this lecture is that a three-dimensional method of lines is very computationally intensive, very slow, and in fact it's rarely seen in the literature. But it can be done, and you've seen the formulation, and having been through transfer matrix method and rigorous coupled wave analysis, you can visualize the implementation. But a much more practical and much more commonly seen implementation of rigorous coupled wave analysis is a two-dimensional method of lines. So let's step through that. We have the same starting point. We have our 6 Maxwell's equations that come from the curl equations. We approximate x and y with derivatives, finite differences, and we leave the z derivative analytical. So same starting point as the 3D method of lines. But now we're going to say that the y direction is a uniform direction, and we will restrict all propagation to be in the xz plane. So since the device is not changing in the y direction, and there's no power propagating in the y direction because we've restricted propagation to the xz plane, then any derivative we calculate in the y direction must be 0. Well, then we go back to those 6 matrix differential equations that came from Maxwell's equations, and we set all of the y derivatives to 0. And we end up here. And it shouldn't be surprising what happens next. What happens next is that our 6 equations have decoupled into 2 independent modes. One we'll call the E mode, and one we'll call the H mode. And so here I've color coordinated it. So the red equations will correspond to our H mode, so they contain EX, EZ, and HY, and none of those terms exist in the blue equations. Likewise, the blue equations, our E mode, contains HX, HZ, and EY, and none of those terms exist in the red equation. So now we divide them by color, and we see we have 2 independent modes, E mode, H mode. Similar to how we applied fast Fourier factorization to improve the convergence of rigorous coupled wave analysis, we can do a trick here to improve the convergence of a finite difference method. And what we'll see, if we have an interface, it helps us a little bit sometimes to sort of blur the boundary between those two materials. So in place of our standard epsilon matrix, which is a diagonal matrix, I wrote it with these little triangle symbols here, meaning that this really is the original epsilon YY, but blurred by 1 pixel, just to slightly blur and average the material properties at the boundary. So we do that for both the permeability and the permittivity. Now for fields that are parallel to interfaces, we want to blur epsilon and mu. For field components perpendicular to material interfaces, it turns out we want to blur the reciprocal of the permittivity or the reciprocal of the permeability. So in fact, it's the X components in this case that are perpendicular to interfaces. So what we end up doing is taking the reciprocal, the permeability, blurring the reciprocal, forming our diagonal matrix, and then taking the inverse of that matrix. And over on this right-hand side for EX, we do the same thing for epsilon XX. So This isn't completely necessary, but it does improve convergence, and this is the equivalent of fast Fourier factorization, but in real space. So our next step now, we had 3 equations for each mode. We want to eliminate the longitudinal component. So for each of those modes, we solve for either hz or ez, and then we substitute these expressions back into the original equations. And now we're down to 2 equations for each mode, and we bring the analytical z derivative over to the left-hand side and all the other terms over to the right-hand side. So we've gone from 3 equations for each mode to 2 equations and rearranged terms a little bit. Now it turns out this is our PQ form, and we can define our P and Q for the E mode this way, and we can define our P and Q for the H mode this way. Notice the blurring to handle convergence is incorporated into the P matrix. So the Q matrices are the same as if we're not doing any blurring at all. But now for our 2-dimensional method of lines, we've reduced this to our standard PQ form. And you know the rest of the story, how to handle that. We handle the layers the same way, calculate scattering matrices the same way, iterate through layers the same way, etc. Nothing's different. So let's talk about handling multiple layers in the framework of method of lines. And what you'll see is that nothing changes. So here's how I visualize a multi-layer device. A restriction is that the periodicity and the symmetry of each of these layers has to be the same. Now that's not an absolute requirement, but it really simplifies things. There are special cases where we can handle things differently. But each layer has its set of modes, the same set of modes as forward and backward propagating. Each layer has its own set of modes, and of course we propagate those within the layer analytically. At the interfaces, we match boundary conditions. So within the layer, we propagate analytically. We match at the interfaces with boundary conditions. So now we completely and rigorously describe propagation through the entire stack. So each layer has its own set of properties, P, Q, omega squared, the Eigen modes. And then from there, we can calculate scattering matrices and then implement our standard scattering matrix algorithm. So how do we derive a scattering matrix? Exactly like before. We look at the fields on either side of an interface. We match our boundary conditions. So these equations that you see here, these are identical to what we saw with rigorous coupled wave analysis. We just know that hiding behind W and V are actually finite differences now instead of our K matrices. We adopt the same type of scattering matrix that we've been implementing in this class, where we surround each layer by a 0 thickness region of free space. So our scattering parameters are calculated the exact same way. And we use a star product the exact same way. We'll set up a loop to go through all of the layers. We star the individual scattering matrices together to get what we call a device scattering matrix. Now when we're done that device is sitting in free space because that's how we've constructed our scattering matrices. If that's not the case, if it's actually surrounded by something else, then we need to calculate a reflection region scattering matrix and or a transmission region scattering matrix and star these together to get our final overall global scattering matrix. And it's from that global scattering matrix that we actually calculate our scattering. We calculate the reflection and transmission side scattering matrix exactly like what we did for rigorous coupled wave analysis and even transfer matrix method. Things change a little bit now when we look at the scattering because our source looks a little bit different and how we interpret the fields looks a little bit different. So the first thing we want to do is calculate the incident field, our source wave. Well, we have our x and y components of the polarization vector. This is for a fully 3-dimensional simulation. And we have the cross-section of a plane wave in the xy plane. And so we have x and y components of that field. We don't need the z component. Well, once we have the field into a column vector, now we can calculate the mode coefficients of our source, or the incident wave. Given these mode coefficients, we can go back to our global scattering matrix and use the S11 and S21 parameters and calculate the mode coefficients of the transmitted and reflected field. Well, once we have those mode coefficients, then we can calculate the electric field that's reflected and transmitted. And then we decompose, for example, the reflected field into X and Y components and the transmitted field into X and Y components. From there, remember we have this phase tilt because we're in real space. We have to remove the phase tilt so that we have only the amplitude portion of the fields in the XY plane. And we did this when we did finite difference frequency domain. Once we have these amplitudes, we can Fourier transform them exactly how we did for finite difference frequency domain. And now we have the amplitudes of our spatial harmonics. So in a sense, by FFTing, we've jumped into Fourier space again, and we now know the amplitudes of our spatial harmonics. We only know the X and Y components so far. So using equations we've derived previously, we calculate the Z components on the reflected and transmitted sides. And of course, once we have that, now we can calculate diffraction efficiencies. And just remember this last equation, this assumes that we are using electric field quantities to calculate the diffraction efficiencies of the transmitted spatial harmonics. If for some reason we're doing H mode, for example, we have magnetic field quantities, this equation doesn't really change other than we replace epsilons for the mu's. But otherwise it's the same. So keep in mind this equation changes depending on whether you have electric or magnetic field quantities. Now I want to give you a very quick comparison to rigorous coupled wave analysis to give you an idea of the differences between these methods. So here's an example device. It's a square array of dielectric cylinders, and refractive indices are relatively low. The highest refractive index is 2.1. And remember I said rigorous coupled wave analysis is best applied when we have low to moderate index contrast. This certainly fits into that. So right away, we're going to expect that rigorous coupled wave analysis is probably the better way to model this device. That doesn't mean we can't use method of lines. It doesn't mean we can't use any number of methods. But rigorous coupled wave analysis is probably the best for this. But let's look at our results. So this top plot was obtained using rigorous coupled wave analysis. And I used 9 by 9 spatial harmonics. That's about where the method begins to converge. And it took almost 2.5 minutes to simulate this. Now we'll notice these reflection spikes, they don't go up to 100%. If we zoomed in on these, we would see triangles, which is a sign that we have incomplete data. And in fact, what we should do is go back in and use more points in the regions of those resonances, and we would see that they probably go all the way up to 100%. But we didn't use enough frequency points, and this is what we have. Conservation of energy looks really good. Everything looks pretty good. Other than that, we haven't used enough points in the vicinity of the resonances. Now let's look at the method of lines. I used lambda over 10 resolution, which ended up being 19 by 19 grid points. This would be roughly equivalent in RCWA using 19 by 19 spatial harmonics. This took over 3 hours to simulate, and it looks a little bit ugly. Notice these glitches. These are going over 100%. This one looks really ugly. This is really due to using too low of grid resolution. If we back off on that, the glitches get much worse. If we go higher in resolution, the glitches get better, but this is already taking 3.5 hours to simulate. Almost 3.5 hours, and it'll quickly take much longer if we went to, for example, NRES being lambda over 20 or something like that. So if there's metals involved or really high contrast, we would find convergence with rigorous coupled wave analysis to be at very, very high number of spatial harmonics. At that point, I think the method of lines becomes an equivalent method, although plenty of people still use rigorous coupled wave analysis to model periodic metals. But if we have that many spatial harmonics, the method of lines can compete with that because it's a real space method and doesn't suffer from things like Gibbs phenomenon that rigorous coupled wave analysis does. But for dielectric structure like this, it's almost silly to use method of lines, but we can and we did. And we see that we're getting really the same answer with some glitches due to the resolution. And so method of lines is a bit more sensitive to the number of points in the grid.